Hello, community. Today, we operate at the fringe of AI research. We're going to have a look at 6 brand new publications from Apple, Google Research, Google DeepMind, a lot of universities. And the overall topic will be reasoning. We know how humans reason. We know what transformer architecture can do. And the question is not, can your AI system reason? But the question is how to improve the reasoning of AI system. And the first important step happened here in February 2024 with Apple. Apple and Georgetown University, and please note here the Department of Linguistics, developed a new context benchmark. Finally, we have new evaluation data on a more focused on a more critical semantic understanding, a context understanding of LLM. With this new contextual understanding benchmark, they not only created this new benchmark to understand here the context problem and challenging of LLMs, they developed here from the linguistic department 4 distinct tasks here in the benchmark from 9 datasets, and we will have a look at this in detail. So, co-reference resolution, implicit discourse relation classification, dialogue state tracking, and query rewriting are the 4 new linguistic tasks. Then you have here the dataset that they used for this, and they evaluated already system to find out what is the reasoning capability today. And you have here the explanation what each and every of these tasks is about. They evaluated the LLM performance on in-context learning and our prompt structure where we provide additional information. So, thorough evaluation of LLMs, focusing on their in-context learning capabilities, highlighting the current limitation of current pre-training approaches for some nuanced context comprehension. So what they did, they primarily said, hey, how good are our pre-trained LLMs? Do our pre-trained LLMs have to have a minimum amount of reasoning ability, of context ability, of in-learning capabilities to go on further to be fine-tuned? And I think this is a beautiful investigation. Now, for my younger viewers here, very simple graph. You know, when we create an LLM, we have a pre-training phase. After the pre-training phase, we have a supervised fine-tuning. And after the supervised fine-tuning, we have a DPO alignment phase where we align the behavior of our large language model, for example. This is the classical route. Now, what they did, Apple said now, hey, for our business case, we know how people use our email. We know how people use our product. So let's say there are 50 ways how people use Apple email. Now, simple. You have to find the perfect ICL prompt if you want to inject here some AI capabilities in the next Apple operating system. So they were looking here for ICL prompts operating on a pre-trained system and ICL prompts operating on a pre-trained and fine-tuned system. Just to note, for the moment, it is not important how this prompt is generated. You can sit down as a human and type your prompt. You can use a programmable interface like DSPy. You can have here the retrieval augmented data, or you use any template from any chain that you like. You find on the internet a simple prompt, or you have a call to a SQL or a NoSQL or whatever you have. Maybe you have a knowledge graph structure. It doesn't matter, because all we are focusing on is I have an in-context learning prompt with a few short example where I show here the reasoning structure that I want. Is the system able to understand the prompt? And now I know the AI reasoning is not primarily based on the retrieved augmented data. So whatever happens here on the right side is not as important as the ability on the LLM on the left side to understand here the reasoning pattern. Imagine you have a training data set, how to pre-train your LLM. And in this data set here, you have, for example, a complexity level of your reasoning training sentences of 2 out of 10. But the ICL prompt that I type now, and I provide 2, 3, 5 examples in my ICL prompt, I give you here a reasoning complexity of 5 out of 10. So how should a system that is pre-trained of 2 level should be able to understand the complexity of an ICL prompt level 5? It will not happen. So independently, what happens here, how the prompt is created, how the example prompt is created, how the perfect vector store prompt is created, if you do not have the corresponding LLM on this side, on the same training level of complexity of augmentation, or in the case of Apple, of context understanding, the system will not work. Let's look at the benchmark data. So here we have our 4 tasks, beautiful, our data set, our metric, and then Apple shows us here the pre-trained large language model with an in-context learning prompt structure. And they go here for a few short results of 2 open source models, here the Llama and the OPT, plus here ChatGPT. This in blue are pre-trained, and then they give us as an additional benchmark here the fine-tuned LLM. Unfortunately, they just give us here the best fine-tuned model for the task, but they did not specify if it's now the ChatGPT fine-tuned or the Llama fine-tuned. Well, I guess it is ChatGPT fine-tuned, but I do not have this data, since it is not published by Apple. Beautiful. Now, let's look at this data in detail. One of the 4 tasks, I choose here the query rewriting here in car with a specific metric. Look, the small opt model goes from 3, 28, 30, 49.6 here in this new benchmark data. And the size goes from 0.1 to 2.7 billion free-trainable parameters. This is what you expect. The system gets bigger and bigger, and the complexity, the reasoning complexity, is able to solve more and more tasks. Now, interestingly, it found here, the study, that as you can see here, we're at 2.7 billion. From the Llama, we need a 7 billion, more than double the size model to achieve here the same benchmark result in the reasoning part. But then the Llama from 7B to 13B to 30B goes from 50, 56, 64. And then here, ChatGPT tells us, hey, I can achieve here a jump from 64 to 83. And the fine-tuned model says, hey, I'm at 95. So you see here, look here in detail at each specific row column combination if you need your system to perform. Just let's make it clear. Although this is here in the context understanding benchmark, the reasoning that we are talking about here in the context of AI encompasses here the model's ability to draw inferences, to understand here a relationship, and to make decisions, if you look at the robotics, vision language action models, based on the information provided, based on the information detected here via sensors in their environment. And this often requires here the integration of complex contextual cues and knowledge. A robot has to identify all the objects that it sees in an environment, so therefore this methodology of increasing the reasoning applies from language model to vision language model to robotic model. Beautiful. Now I understand, you remember that OpenAI offers here very wealthy companies to pre-train the GPT-4 system on their corporate complex data structure. And at the time hearing this, I thought, hey, why is it not enough just to offer here to fine-tune their GPT system on their corporate data? But now I understand that the pre-training quality, that the complexity level of the pre-training system is determining where you start with your reasoning capabilities. And then, of course, with DPO, you have, for example, a medicine pre-trained or a finance fine-tuned GPT-4 ICL with some great performance. Let me give you another example. Imagine you're a hospital and you go there to OpenAI and you have a lot of money, and OpenAI offers you to pre-train their GPT-4 system on your complete medical data, on all the diagnoses, on all the doctors in your hospital did, subscribed, performed, how the illness behaved over years. So this is really important pre-trained data. And then you also say, hey, let's say 3-4 times a year, you have an additional fine-tuning with bringing in new data from the last month. So you integrate the new data, the new knowledge into your weight structure of your system. You do this, that your every day, your daily new data performance, your superior ICL performance now is there if you need now daily complex tasks. I think this is a beautiful idea and suddenly shines the light here on the pre-training data quality for complex reasoning. Because if the training data do have a complexity level of 2 and your ICL prompt has a complexity level of 5, you can imagine what happens. Okay, very fast. The pre-trained model, beautiful generalization, have in-context learning limitation here, especially for complex co-reference chains, and have a dependency on the training data. So if the pre-training data lacks the sufficient example of complex contextual interaction, if your training data are just a copy of Wikipedia or just a copy of all the books in the world, you are not getting the complexity or argumentation capability you are looking for. You have to design those data sets for the pre-training phase. And yes, now it gets interesting. Okay, for the fine-tuned models, clear, we have a specialization and adaptation to complex contextual features, but only within the fine-tuning domain, within the domain knowledge. We have a reduced generalization and data and resource intensive, since here, for example, the fine-tuning of each model here for a specific task or a group of specific tasks demand more and more compute resources. And of course, you want to have the best of both worlds. You want to bridge here the discrepancy. You want to have an augmenting pre-training with task-specific logical augmentation data. You want to integrate a more diverse and a more complex contextual scenario into your pre-training phase. So we have to pre-train our LLM in a different way, inside number 1. And then you want to have adaptive fine-tuning strategy. And this allows here for a transfer of knowledge between here our fine-tuned task. And if you want to explore here this hybrid approach, well, of course, you want to combine the strength of the pre-trained models with the specific fine-tuning abilities through techniques like prompt engineering or dynamic adaptation. And you might say, hey, what is this? Yes, you know it is DSPy, and I have a whole playlist on DSPy. Beautiful. So therefore, short summary, first paper, I have to accelerate. Context as a foundation for reasoning, and diverse reasoning tasks are important here for a better benchmark result. So each of those tasks that Apple looked here at in a form of reasoning, so from identifying reference in a text to understanding the implicit relation between discourse units and adapting dialogue responses based on the state and context, is now shining a more focused light on the reasoning capabilities. And this Apple benchmark is important. It gives us here the access to the understanding of the next papers. Beautiful. New context understanding benchmark by Apple. Great. Now, let's focus here immediately on the next paper. You see here, University of California, Carnegie Mellon University, and University of Waterloo. They focus here on the pre-trained language model. Yes, what a coincidence. And yes, I have chosen here the paper in a specific order for us to learn this. And they say, hey, we can view here a large language model as deriving new conclusions by aggregating indirect reasoning paths seen during the pre-training time of our LLM. So you see, we are here suddenly in Raft theory. Beautiful. But they now focus here on the pre-training time, like Apple did and showed us the importance of a complexity level adequate pre-training dataset for the later queries that I have on the system. For my younger viewers, I try here something new. In green, I write here the simple explanation I come up with, and on the other side, non-green, you have a little bit more in-depth explanation. Let's try this. So, you see, the findings are from this new study that the reasoning abilities stem from their pre-training phase of LLMs, and the fine-tuning serves only as a mean to enhance this existing reasoning capabilities further. But without the pre-training ability, fine-tuning is not at all efficient. And this insight challenges here the conventional understanding of fine-tuning as a way to teach LLM new abilities, suggesting instead that it only refines and optimized here some pre-existing capabilities that were generated in the pre-training phase. Yeah, you have it here a little bit more complex. So what they do, they formalize here reasoning path as random walk path. We know this from mathematics. In graph theory, you have random walks here on some knowledge graph or some reasoning graphs, and they suggest here that the weighted sum of all of these path probabilities can explain here maybe new added language model reasoning processes. So very clearly, we go here on a random walk idea on latent reasoning graphs. And to be more specific, they here say our method assumes a chain of sort paths can be viewed here as random walk, as sampled from a reasoning graph, where the node of this graph represent now reasoning states. Now, you know that here the state is here more or less the content of a node, and by clustering similar reasoning states and performing here now our multiple random walks on this latent graph, new reasoning paths are generated for training. And these new paths that we discover with this methodology aims to enrich here the exposure to diverse reasoning sequences. If this sounds complicated, no, not at all. This is exactly what I showed you here in my video DSPy5, when I showed you if I have here a new astrophysical publication, and I told you, look here, I saw this sentence is important, and I read this sentence, and I say, if I combine it with this sentence, and here we have a nonlinearity, I've come to the logical conclusion. I understand what is the content of this paper. And you remember, I told you that this storyline is also a graph. And now they just formulate it in a more mathematical way, but this idea we already explored weeks ago. So, chain of sort paths viewed as random walks from a reasoning graph where the node represent here our states. Let's jump to the next scientific paper. Here we have here the Nanyang Technical University in Singapore, the Institute A* from Singapore, and Salesforce Research. Beautiful. What they did is they established a framework to learn a planning-based reasoning through direct preference optimization, our beautiful DPO alignment, on some specifically collected trajectories, which are ranked according to a synthesized process reward system. So you know we are going now to learn new policies. And in this specific paper, we will crank up here the compute intensity for this methodology from 20 to 80 of 100. So let's just jump right into it. They argue that LLMs have demonstrated significant potential in handling complex reasoning tasks through a step-by-step rational generation. However, recent studies showed that there are concerns regarding hallucination and flaws in the reasoning process. Something is not working at all. And now you see here's another group of experts working here on this reasoning, but now on a planning-based reasoning by trajectory collection and here a policy optimization. So they go now not only on the pre-training system, but on the other end of the spectrum, and they focus here on our direct preference optimization of the policies. Beautiful. So in green here, this is for my grasshoppers, a new method for making LLMs, like those used in AI to understand and generate language, better at reasoning and explaining their thought process beyond what we have today. The goal is to fix two main issues. The first is stop hallucinating, and the second is teaching those models to reason correctly. And they say it is very time consuming if you do the human side DPO. So we have data normally by a lot of human input, and the system learns here or mimics here this human behavior, but let's do this in a more efficient way. Okay? On the other side here, we have a synthesized process supervision with backpropagates, the ground truth outcome supervision to intermediate states. Yeah, we collected the seed trajectories from our LLM, operating the LLM to learn a better policy for generating reliable rationals through our DPO alignment. And the process rewards are synthesized now without requirement teacher models or any human additional annotation, significantly reducing the cost and the complexity of the training process in this particular topic. So, easy. DPO works by guiding the AI to learn from example of reasoning that can lead to the correct answer. The AI can practice some reasoning task by trying out different paths. You see here again the path idea, or sequences of logical steps that the AI might take to see which one leads to the right conclusion. So in the very simplest term, they just try it out. And by trying it out, the AI learns and develops here a special policy. It learns which paths are more likely to be correct based on the outcome of this practice attempts of this learning dataset. Now, you might see it is not as simple as it sounds, because the approach here is grounded in a sophisticated understanding of the reasoning process, combining three elements. The first is here a Markov decision process. Then we have here Monte Carlo tree search for the planning. And you notice the reinforcement learning, our RL, for policy optimization. So now, as I told you, we have here a much more intense compute regime, because Markov, Monte Carlo, and reinforcement learning is going to happen in sequence. Now, if you're new to AI, a Markov decision process is something we know in mathematics for centuries. And Monte Carlo tree is something that we know that when I studied theoretical physics, I did my quantum corrections here with Monte Carlo simulations. Give you a very easy example, a logical reasoning task. Imagine an AI's task here with solving a logical puzzle. It must now decide on the sequence of steps that it leads to the correct conclusion. So think of the puzzle's condition and the possible conclusion form now the state of our system, and the reasoning step the AI can take are now the actions. So we have now our three elements here in detail. Have a look at this. Or, very easy other example, if you have a puzzle and it involves deducing here who owns a zebra based on a series of clues, you use here 1, 2, 3 steps to find out how it works. So now to the real world examples. So what they do here is learning here the planning-based reasoning via trajectory collection and process reward synthesis. So step 1 is easy, trajectory collection. You have a context, you have a question, and you have options. And then you start with a particular policy model pi. Beautiful. There you have sort 1, action 1, observation 1, sort 2, action 2, observation 2, and whatever is your list that goes on. Second step, you collect now the raw expected values of those intermediate steps. Sort 1, action 1, observation 1. Beautiful. Explore and play. Beautiful. So you go through this and you sample partial trajectories. Step 3 is you train here a process reward model on the data from the collected expected values via classical way across entropy. So you have now a process reward model. Step 4, annotate the full trajectory from pi with the trajectory level rewards by accumulating here over the different steps. And then, step 5, you optimize the policy model on the trajectory pairs via our DPO modeling. So we combine here a lot of possible ways to go forward, possible ways of sampling here our partial trajectories, and then we just calculate, if you want, the probability and find the best way forward. Great. Now, if you do this operationally, if you really code this, be careful, because if you look at this, the team did it here with multiple LLMs, with a Llama 2 70B, with a Mixtral, mixture of expert, 8x7B instruct with ChatGPT and GPT-4. But they had to start somewhere. So, in order to simplify here the evaluation procedure for the model without task-specific fine-tuning, they use here a one-shot prompt of the React template, which is the same that we used for collecting data to induce the model to generate reasonable solutions. So, think about this. This here is the prompt that now GPT generates 10, 20 similar prompts for. So if you print money, if you are a national bank, remember, this is the plate to print your money. If there's any mistake here in those 14 or 15 elements of sort, observation, action, if this is not the absolute perfectly constructed prompt, everything else in this system is derived from this one-shot prompt of React. So put a lot of idea and validation into your specific prompt for your specific task, because this really is important. If you make here one mistake, it will be all over the system. Great. So we at the authors first sample some responses, 10 to 20 or whatever you need, from larger LLMs, ChatGPT, GPT-4, following the React format for the knowledge distillation. Since we cannot directly fine-tune a GPT-4, yes you can, but you have to pay a lot of money, due to the resource limitation of this team. Beautiful. And after that, the authors observed here that they can obtain now a smaller LLM with some considerable reasoning capability through a supervised fine-tuning. And now this supervised fine-tuning model serves as the new baseline and as the new foundation model for the next step where we have our DPO training. So, short summary. The first method was to find indirect reasoning paths in pre-trained model. Then we went on to synthesize here process rewards here in our DPO optimization. And now you, as a subscriber of this channel, might say, hey, wait a minute, what do you think about this idea? Instead of some continuous augmentation, let's build some atomic reasoning modules, such as critical thinking or step-by-step thinking, and compose them into a complex graph structure. So we define here the reasoning module as the nodes of a possible augmentation, a reasoning graph. And I would say, hey, you are genius, Because, you know, this is exactly what Google DeepMind and the University of Southern California did just days ago. They published here Self-Discover. But before we have to read this paper, please remember there was by Google DeepMind here this pre-paper, and this was on Prompt Breeder. And just to give you a short summary, Prompt Breeder was a self-referential, self-improving system that could automatically evolve effective domain-specific prompt generation for a particular domain at hand. So, Prompt Breeder was self-referential in that it not only evolves here the task prompts, but it also evolves here the mutation prompt that govern the way that the Prompt Breeder modifies the task prompt. So, in short, not only improving the prompts, but also improving in the way that it is improving the prompts. Beautiful. So we have a research paper number 7, but I'm not going to explain you number 7 because we have only 6 paper I'm going to explain. But now you get the idea here. Beautiful. So it's a simple 3-step approach. At first, for a particular query, you select your reasoning modules. And then we adapt those reasoning modules here for our specific query. So each of our module, we add a little tiny degree of freedom to this system. So it can wobble a little bit around in the decision space. So it can adapt to the task. And then we implement this reasoning modules here, a chain of selected reasoning modules here in a step-by-step reasoning plan. You go with JSON or whatever you like. Now, very easy for our greenhoppers here, grasshoppers, enabling here the language model to autonomously compose the reasoning structure, given a specific query, thereby significantly improving the performance on complex reasoning tasks, a self-learning system. And as I told you, autonomously identify and integrate reasoning structure in this 3-step model, select, adapt, implement. Now, here, they use a limited amount of reasoning modules. They have here 39 reasoning modules consisting of high-level cognitive heuristics for problem solving. And this list is here generated exactly by the Prompt Breeder. So you have a complex query, and now you have reasoning modules, and you know reasoning modules. One is 38. Let's think step by step. You know this. Or are there key assumptions underlying the problem? Or what are the potential risks and drawbacks of each solution found? What are the long-term implications of this problem and this particular solution? You have the critical thinking module. You have the creative thinking model. You have the use system thinking model. You have risk analysis. You have reflective thinking. You have what is the core issue of the problem, what needs to be addressed first. So this 39 modules Google identify here as their primary elements in their toolset. And this is something real beautiful. Yeah, this is the easy explanation for you. So as I told you, by amalgamating now these basic reasoning modules into a structure, into a structured reasoning process, they could enhance here the reasoning benchmark, achieving up to 32% improvement over traditional chain of thought and surpassing the chain of thought self-consistency benchmarks by over 20% with 10 to 40 times less compute. This is really an achievement. So, again, for our grasshoppers, select, adapt, implement. Beautiful. And here you have the benchmark data. And here you see that this self-discover, the last one here for a Palm 2 large model with self-discover, you see it really outperforms the other models. Or they did it also here with a specific focus on GPT-4, which is interesting for Google, with self-discover. And you see the jump from 73 to 81, or from 53 to 85 is really significant. Now, of course, if you discover this reasoning structure, that is grounded in those 39 atomic reasoning modules with a little bit of wobble around. This is benefiting from the strength of multiple reasoning modules in contrast to applying only a single module like the chain of thought module. So the more models you have, the more complicated it will be. But where's the sweet spot? Where's the Goldilocks zone? That's an interesting thing. And I think we can optimize this further with DSPy. But this would be the content of the next video, or one of the next videos. Beautiful. And now for another paper. You see here, what we are, University of Sydney, Nanjing University of Science and Technology, Yunnan University. And they have here LLMs as an indirect reasoner. And here we make indirect reasoning is a methodology in logic that we know. And here we make use of contrapositive and contradiction for automated reasoning. It's a little bit more on the mathematical logic side, but really interesting. So, short summary, a novel indirect reasoning methodology for enhancing here the LLM capability in complex reasoning beyond the limitation of conventional direct reasoning approaches, like we know, the chain of thought and the self-consistency. Now, how is this done? They have here the logical construct of the contrapositive, and explain this in a second, and the contradictions. And they have two primarily phases. In the first phase, you have here the contrapositive to expand the available data set and the rule set. And B, we have that we instigate here the indirect reasoning through a proof by contradiction. So this is not that easy, so let me give you the example. Here on the left side, you see the direct reasoning path. And on the right side, you see the indirect reasoning path. And here the instruction for the indirect reasoning is the following. Proof by contradiction in logic and mathematics is a proof that determines the truth of a statement by assuming the proposition is false. Then working to show its falsity until the result of that assumption is a contradiction. This is what we know from mathematical proofs. Maybe you are not familiar with this, but this is in the logical biosystem a powerful tool that we use here, but it is not a simple tool. So for my green grasshoppers here, a contrapositive switches and negates both sides of a statement. So if we have the origin if A then B, now we have as a contrapositive if not B then not A. And a contradiction involves proving something is true by showing that assuming the opposite leads to something that is not possible. Yeah, beautiful with examples, you have it. Or if you want here again, what is let's start with the indirect reasoning, a method in logical mathematics, where the truth of a statement is established by demonstrating that its negation leads to a contradiction. So indirect reasoning often involves assumption, assuming the opposite of what we are trying to prove, and then showing that this assumption leads to an impossibility, thereby proving that the original statement must be true. And proof by contradiction, what we apply here, is a specific form of indirect reasoning. So in a proof by contradiction, you'll start by assuming the opposite of the statement you want to prove is true. Through logical deduction, if this assumption leads to a contradiction, a situation where something is both true and not true at the same time, then the original statement is proven to be true. This method is based on the principle that a statement and its negation cannot both be true. Beautiful. And then you have direct reasoning. Great. So what you want, of course, you want here the best of both worlds. So you want to combine both methodology, the direct and the indirect reasoning, and they have shown in this publication that this offers the best of both worlds. Beautiful. Yeah, if you want to have here a simple visualization, stage 1 or phase 1 is rule augmentation, and phase 2 is then the indirect reasoning. Here, in simple terms, explained again, rule augmentation and indirect reasoning. in some complex and multi-step reasoning scenarios, this indirect reasoning helps language models to reach the answer with fewer steps than direct reasoning in many circumstances. So you even have an optimization of your logical construct. And here the rule augmentation, as you see here, augments here the body of available rules here. So here you have it. Now we have a fourth methodology. Now a novel indirect reasoning method that employs the logic of contrapositives and contradiction to tackle here indirect reasoning tasks. Now, as a personal statement, I would like to say that humans are not really good at applying mathematical logic to their reasoning. And if something goes wrong here in applying contrapositives or contradiction into the logical path, humans not immediately see this. So I would be a little bit more careful implementing this methodology, but the other three are just beautiful and straightforward. And finally, let's end this with the sixth paper here. And we had the beginning, the first paper here with a new benchmark. And now we end this here with also a new benchmark. And a new benchmark for reasoning chains. And those reasoning chains are now analyzed in detail, because the idea is a chain of thought is as strong as its weakest link. So chain of thought, beautiful. Accurate reasoning here is important, but the recent literature, and we are here in February 2024, shows here they want to find automatic methods to verify all the little detailed reasoning steps, want to evaluate each and every step and improve on their correctness. So it is not that you have a query and you get an answer back and you verify this answer, but you want to have a look into your large language model, into the causality routines, into the reasoning routines that the system applies, and verify each and every step in this routine. Yeah, they call it reveal, reasoning, verification, evaluation, novel data set, and a novel benchmark. Finally, new benchmark data designed to advance the evaluation and the verification of chain of thought reasoning in LLMs for more complex open domain question answering tasks. Beautiful. What they found, to make it very short, they are complication across various dimensions, including world knowledge inference, specialized knowledge, and logical consistency. This does not really work, they found. There's a problem. And revealed by this group showed us, or highlighted here, a notable discrepancy between the LLM's ability to accurately attribute information also to external sources, and in particular to maintain logical coherence within the reasoning chain, within your chain of thought. And if the system does not keep a logical coherence within one reasoning chain, the whole system breaks apart. So you see, there are greater challenges here in logical correctness, factual accuracy, and so on. So here you have it. Now this is a very short summary. We have here real challenges for LLMs with this new benchmark data here to accurately attribute facts correctly, also to external sources, and to maintain the logical coherence within reasoning chains. And if we do not achieve this, we have a problem that our systems are not really working in the optimal way or form. Just to give you here an idea, if you are in currently second week of February in AI development, you are still focusing here in this domain. However, AI research moved on. Let me show you this on a practical example. Here I generated this image with GPT-4, exactly here for this reveal, a fine-grained approach to verify each step of a reasoning chain for correctness. And let me show you how GPT-4 did this. And I said, hey, create an image in 3D of logical coherence. And I, as a human, I would have no idea what to depict. So ChatGPT-4 came back, and here you have the complete argumentation, the logical deduction that ChatGPT-4 tried to understand my logical coherence term and step by step build up here the prompt for the image generation. And here you have the prompt now. And then from this prompt, this image is generated, and here we have the, if you want, headline for the image. So you see, this is happening also not only on the language model, but also if you want to create here text to vision images, or if you want to understand an image, you see the logical deduction chain that is happening inside of GPT-4, for example, is not trivial and it is not optimal, because I have found areas of instability within GPT-4. Okay, now if you think the money involved here, and just here from Yahoo Finance, AI data management market will be worth $70 billion in 2028, or AI healthcare market, $148 billion in 2029. This is significant. But you know what? Now we have, in the first week of February 2024 at least, an idea of how we're going to tackle this. Because, easy example, think about a traditional medical doctor in a small village. And then think about the other side of the spectrum here, about an ultra-modern Dr. House artificial intelligence system. Now, we can use now our understanding from this video to exactly define here the level of complexity for each of these offices. Think about it. Here in the traditional medical doctor office, I have no idea about traditional medical doctor tasks that they do, but let's assume for simplicity they have 100 tasks. So every patient that comes in, they find one of 100 tasks, of 100 ways to treat the patient. So what we have here the peak that is really statistically, almost everybody has 1 in 100, let's say, illnesses here in this small town. But this has a low complexity. So if I build an AI system for this particular case, and I know that it's always the same, they have a cold, they have a flu, they have something, they broke a leg, whatever, this has a low complexity. And whatever this doctor is not able to treat, to analyze, to have a diagnosis on, it goes to a normal hospital, and from the normal hospital, you know, it goes to Dr. House. Now, if I build an AI for the Dr. House AI support system, I know exactly where I have to look for. I have to look for the high complexity classes and the long tail of the distribution. I have to look for logical correlation in a really, really low probability vector, because I know that everything else has been already investigated by the classical medical doctor in the normal hospital. So I know that I can, if I create now an AI system for this, I just have here, I don't know, on the right side of the screen here, a continuous list of possible combination and of possible, I don't know how to say this, combinatorial diagnosis elements, so that one might contribute to another one, but I'm looking for the low probability ones. I'm really looking for 1 in 1,000 that it's gonna happen, you know? But this information here, this long tail here, is important for my Dr. House AI. And now you understand what I mean if I say you have to watch out carefully for the complexity class of your application, of your AI system that you want to build, because your complexity can be completely different and you have to take care to choose the right one.